Thanks very much. I'm sorry to miss the opportunity to be physically in Korea, so I hope that I get that opportunity again soon. So today I'll tell you about constraints on axions and emergent symmetry. This is work that will appear shortly with Daniel Brennan, and I've also highlighted a few additional papers that are important, at least the list of authors. And I'm happy to discuss. There are many other works sort of in the. So what is this? Oops, what happened? Okay, we've already had some technical problem. Okay, so what is this work about? So we'll be studying axions. So an axion is a field A, which is a periodic scalar. So A will be identified with A plus 2 pi n f, where n is an integer. And of course, axions are ubiquitous in all sorts of models. So all sorts of models of beyond the standard model physics, string theory, etc. And the basic hallmark, the basic kind of action we're going to be studying is the action for axion Yang-Mills theory. So what does it look like? I'll just write it down once and for all. We've got a standard kinetic term for both the gauge fields and the axion. And then the interesting thing is that there's a coupling between them. And of course, the coupling to the gauge field like that is possible because instanton number is quantized. So 1 over 8 pi squared integral, here I'll switch to the more convenient differential form notation, trace f wedge f is in the integers. And here, throughout this talk, I'll be imagining that SUN Yang-Mills for simplicity. Okay, so what is it that we want to say here? What are we going to study? So the first thing I'd like you to note, so obviously all of this is extremely familiar, and also so is this observation, that axion Yang-Mills is a non-normalizable theory. So, you know, the f wedge f term has dimension 4, A has canonical dimension 1. So that's some dimension 5 operator, this A trace f wedge f interaction. And so we could ask, what happens for large energies? So here what we will need is some kind of UV completion, something that comes in and fixes up that dimension 5 operator. So a kind of standard thing that might occur, which we'll discuss a little bit later in an example, is that, for instance, in the UV, the axion A might equal log of some complex scalar, or sorry, rather the argument of some complex scalar, with the value liberated at high energies. Okay, so what we're going to do in this talk is we're going to think about this question. And what we're going to do is we're going to derive well, since it's a talk, I'll more like motivate, but the paper derives model independent. So this will be the key phrase, model independent constraints on UV completions. And you will see exactly what I mean when I say model independent constraints on UV completions as we go along. Okay. So to begin, we need to discuss symmetries of this theory and scales that are present in this theory. So I'd like to formulate nicely the thing that we're going to prove, and I'd like to do that by considering various dynamical objects and symmetry scales in models of axions. Okay, so the very first thing to consider is that axions have strings. Everybody knows this. How do you think about a string in an axion model? Well, you can take the contour integral of dA around some curve, some closed loop, and around a string, instead of being 0, that will be 2 pi n f. So what's the picture? So we'll have a string here at the origin. This is the transverse space. We're in 4 space-time dimensions, so the transverse space to a string is 2-dimensional. And then that makes a natural little 1 cycle here that we're integrating over in this contour integral. And this n you can think of as the conserved string charge. So one thing that you see from this is that the so-called axion decay constant which is F, this sets the scale of the string tension. So we expect that string tension, T, at least the square root of it, is proportional to F. Okay, so in the infrared, these strings have infinitesimal thickness. So we can think of them as defects. And associated to that, this string number n is conserved. As we get to the, this may no longer be the case. So in the UV, dynamical processes manipulate conservation of string number. Let's associate a scale with that. So we'll call that scale where it occurs E2 form. And so far, this is just some mysterious name. So the name will be explained later. And what we think about E2 form, so this is the scale where the strings above which the string number is no longer effectively conserved, and we think it should be less than F. After all, that's the tension. But in some models, these can be far separated. Okay, so that's one scale that we can talk about when we talk about a normalization group flow from some ultraviolet model to an infrared model that terminates in Axion-Yang-Mills. We can talk about this scale E2 form, where the string number starts to be conserved.
Sorry, Clay, can you explain which string is, sorry, Clay, can you explain which string number you mean? There is no string conservation charge in this theory.
Sorry, I mean just the integral of the as I'll explain later, the two-form symmetry.
But that doesn't act on strings, that acts on branes.
That acts on string defects. Right, this theory has some kind of defects around which integral of dA is 2 pi nf.
I think a two-form symmetry acts on one-form symmetries in 4 dimensions act on strings.
No, these are non-dynamical. The associate, so there's also an axion domain wall that terminates on the string.
Yeah, that's the object that actually exists. What you're talking about is not an object in the theory.
Well, okay.
There is no conservation number of these things. They don't exist.
You're trying to say that the sector n has to be 0. I mean, you can also consider axion domain walls and the same thing will occur.
I think that the objects that exist are branes. And you can talk about their conservation laws. But these objects, I don't understand. They don't exist. So
Well, the axion has a two-form global symmetry, as we'll discuss.
yes,
And
that's branes. That acts on branes in the Hilbert space.
no, Zohar, you're confusing defects and states.
You're trying to talk about the endpoints of the branes or something like that.
Yeah, just like in the one-form symmetry, you will talk about Wilson lines, which are the terminus of string worldsheets.
Yeah, you are trying to talk about.
So I'm talking about strings, which are the terminus of axion domain walls.
That's right, but there is no question. There is no notion of conservation there. Conservation is something that happens for objects that have finite energy that exist. And
there's a conserved quantum number. There's a conserved two-form global symmetry in this problem.
Okay. It's like you are talking about some conservation of a quark number in a joint UCD. I don't understand what it means. There are no quarks in the fundamental. So it's a
But it's a non-dynamical defect. It's like saying that the n-ality of a Wilson line is conserved in.
Okay, so you're basically talking about conservation number of this brane number. The
Yes,
brane number
yes.
Okay.
Yeah.
Thanks.
Yeah. Sorry for the confusing language. I think maybe I'm trying to say it in an easier way, which is maybe more confusing than what I mean. But to be more clear. If I were talking about Yang-Mills, which I'm about to talk about the Yang-Mills sector, there's a one-form symmetry where the n-ality of the Wilson line, the n-ality is conserved and the charged object is the Wilson line. The analogous object for the two-form symmetry is the string. Okay. So that aside will lead us naturally to the other symmetry that we need to discuss, which is SUN, the symmetries of SUN Yang-Mills theory. So this has another interesting quantum number. And I will say it more precisely in terms of some fancier language in a minute, but I'm just trying to introduce the inequalities and the results. So this quantum number would be non-zero on Wilson line operators. So we'll have some line here. It's an operator. It's in some representation of SUN. And the conserved quantum number is the n-ality, which you can think of as the charge under the center which is also equal to the number of boxes in the Young tableau mod n. And this is conserved. This is conserved. Why is it conserved? Well, it's just because there's no fundamental matter. To screen such a defect. Okay. So because of this symmetry, we can also introduce another scale. So an ultraviolet model of axions typically has fundamental matter. Which violates the symmetry, which violates this quantum number. So there will be some scale, which I'll call E1 form, which we can think of as effectively the mass scale of charged matter, charged fundamentals. Okay, so now we see that if you have a whose low energy is axion Yang-Mills, and the UV is unknown to you, then associated to such an RG flow, you can introduce two scales, E1 form and E2 form. Now, what is our result? Our result can be phrased in terms of these scales. So the result is that in any UV completion, we have that E2 form is greater than or equal to E1 form. Now, I should really clarify a little bit what I mean here. E2 form and E1 form were defined by saying, below some scale, E2 form or E1 form, some quantum number is conserved. Of course, that's an approximate notion. So these energy scales are only defined approximately. So you could ask, what does it mean to have an inequality among approximate quantities? What it really means is that the opposite is impossible. So E1 form much greater than E2 form. This we can make sense of even if they're approximate scales, is impossible. If the IR is axion Yang-Mills. So impossible. Now, okay, so that's the statement of the result, and it's a very simple result, but it's a little bit cute. So what I'm going to do is try to, for the rest of the talk, try to explain to you, roughly speaking, the intuition that goes into how to prove such a thing. What is the formalism in which it could be made precise? And then I'll conclude by giving you an example of how it works in practice. Any questions? Okay, so what we'd like to understand more precisely now is what really is full symmetry of axion Yang-Mills. I skirted around it a little bit. And especially in my answer to Zohar, I skirted around it a little bit. But now we're going to get more precise. So we can consider dA is the axion, take its exterior derivative, take star of it. This is some 3 form, mu, nu, rho. This is a conserved 3 form. So a conserved 3 form means that you have naturally a so-called 2-form global symmetry. I'll write it like this, U1 superscript 2. This means that it's a 2-form global symmetry. So we remember how many indices the current has. And the U1, the fact that it's U1, that's because the string is quantized. Okay, so that's a slightly more technical description of one of the global symmetries that I introduced above. Now, what about the center symmetry? So this is really a discrete 1-form symmetry. So again, this reminds us that it's a 1-form symmetry. 1-form symmetry means the charged objects are lines. And of course, this 1-form symmetry has been extensively studied. It's related to confinement. So it's an exciting concept to think about. So what we know is that the IR symmetry contains these 2 pieces. Now, your first thought might be, well, okay, so what? We've got this, this U1 2-form symmetry. We've got this Zn 1-form symmetry. Maybe they're just completely independent. Maybe they don't talk to each other. And one of the things that's going to give us the juice here is that these symmetries mix. More technically, this means that the correct global symmetry is what's called a higher group. If you haven't studied this concept of a higher group global symmetry, you don't need to worry too much. Essentially, what it is kind of an analog of a non-abelian group, but where the symmetries have distinct form orders. So, you know, one possible symmetry group that we could talk about here is Zn1 times U12, and the true symmetry group in this Axion-Yang-Mills problem will be something richer. It will be something where these symmetries are a little bit blended together, where there's some kind of non-trivial structure constants. Okay, so I will give you first the intuitive idea, and then we'll try and make it slightly more formal. So first, the intuitive idea. How can you see that there's something going on? There's some kind of mixing. So let's discuss these configurations that we were talking about. So let's have a picture in space where here we've got an axion string. And coming off of it is an axion domain wall. I'll define that concept momentarily. So this is a picture in space, not space-time. So what does it mean to have an axion domain wall? Across the domain wall, A jumps, so A shifts to A plus 2 pi F. Let me do a charge 1 wall. So if you think about the Axion-Yang-Mills Lagrangian that we wrote down, this implies an interesting action on the wall. So S wall then contains a Chern-Simons term at level 1. That's actually rather interesting from the point of view of the symmetry structure. This 3D Chern-Simons term, or I should say 3D Chern-Simons theory, first of all, it has this Zn1 one-form symmetry. But it also has an anomaly under this one-form symmetry. Whenever you have this kind of configuration where a defect for one kind of symmetry has an anomaly under another kind of symmetry, something interesting has happened. The symmetry structure is not really completely factorized. And that's an example of how to see that something interesting is happening here. So what I'd like to do now is give you some more formal points of view on this phenomenon, 2 different formal points of view, and then we'll use it to derive our conclusion. Okay, so that was intuitive. How do we say things more formally? So more formal, number 1. So one way to think about things is that symmetries are represented by topological operators. What are these topological operators in the case at hand? So this Zn1 one-form symmetry, we can think that this is associated to codimension 2 topological operators. Let's call these operators O sub 1 form of sigma. So they do something interesting to Wilson lines. So for instance, if I draw a picture in space where I have a Wilson line sitting at the origin, this is a picture in space. This is a Wilson line. Looks like an infinitely massive particle that just sits there. And this is O of sigma. So this kind of configuration measures the charge of the Wilson line. So that's just a lightning statement about the topological operators for the one-form global symmetry. What about for the two-form global symmetry? Where in a sense, I already introduced them. So we have this two-form symmetry U1. This should have codimension 3 topological operators. We already wrote them. We can take the integral over a closed cycle, let's call that cycle gamma, of dA. And this we could call O2 form of gamma. And we saw that this measures string charge. So to be formal about the symmetries that we have these two sectors of topological operators. We have the one-form global symmetry topological operators, which are codimension 2, that is, they're supported on surfaces in 4 dimensions. And if they link a Wilson line, they measure the charge of that Wilson line. And then separately, we also have these codimension 3 topological operators, which measure string charge, and they're associated to the winding of the axion around a cycle. Okay, so what can we do with this? Let's consider a configuration where we have 2 one-form symmetry defects. Let's call them O1 form intersect. Okay. So let's try and draw it. Here's, say, sigma 1, on which we have O of sigma 1. And okay, this is supposed to be a picture in 4 dimensions, and I'm not very good at drawing in 4 dimensions. So maybe I'll draw sigma 2. So these are on O of sigma I, and suppressing 1 dimension. Because I'm not very good at thinking in 4 space-time dimensions. But the point is that these are both codimension 2. So the intersections are typically points. And here is such a point. Now, what you can show, essentially just by chasing through this kind of anomaly that I wrote for you on the axion domain wall world volume, is that at this special point, something very interesting happens. Out from it comes a gamma. And on this gamma lives O2 form. So this is an important statement about the fusion of the symmetry defects. So this is a state fusion. So whenever we have a configuration of one-form symmetry defects, they will typically intersect. And when they do, out will pop a 2-form symmetry defect. So this is a statement about the failure of the symmetry to factorize. It is mixed in an interesting way. Okay, I'd like to give you, this seems a little bit abstract. Maybe I'll give you more formal argument number 2, which is helpful for doing calculations.
Sorry, Clay, can you say a little bit more about like what are the group elements for sigma 1, sigma 2, and gamma?
I'm being a little bit deliberately obtuse here, but for gamma, I'm taking the current generator, the dA, and for sigma 1 and sigma 2, I'm taking the generators.
The gamma is labeled by a U1 phase, right?
That's why I took the current.
Oh, you take the current. Oh, I see. I see.
I took the log. Yeah.
I see. Okay. Thank you.
Yeah. Okay, more formal number 2. More formal number 2 is to consider background fields. So whenever you have a symmetry, you can couple it to background gauge fields. And often tricky things like funny fusions of symmetry defects are related to tricky things like funny gauge transformations of background fields. And we'll see that that's the case here. So let's step back for a minute. So remember we had this interesting axion Yang-Mills type coupling, 8 pi squared F trace F wedge F. And this makes sense because instanton number was quantized. Now, actually, that's not really a good enough answer to why the axion-Yang-Mills coupling makes sense. What's the problem? The problem is that suppose we turn on a background I'll call the background B for the Zn one-form symmetry. So such a background, what kind of object is it? So B is some kind of cohomology class. It's an H upper 2 of space-time. This M is space-time with coefficients in Zn. So it's some kind of discrete cohomology class. If you haven't seen this before, you probably have heard of it. It's so-called 't Hooft twisted boundary conditions. That's such a background. Now, what do we want to say? Well, if you turn on such a background, the instanton number can become fractional. So the instanton number what is that? That's 1 over 8 pi squared intertrace F wedge F. Well, what happens? This becomes an integer plus a fraction that's controlled by this background B. So let me write it. N minus 1 or 2n integral over space-time of something called the Pontryagin square of B. Okay, if you're scared of the Pontryagin square, you can think that this is approximately B cup B. It's roughly speaking the square of B. Any case, it's the output of this integral of Pontryagin square of B is some integer. And so we see that there's some kind of fraction here because there's a denominator. Okay, so what's going on? So this is a little bit funny. So, you know, the axion is allowed to have shifts by 2 pi nf as we move around space-time. And that made sense when we had quantized integer instanton number. But now we see that when we turn on the background field for this one-form symmetry, we lose that. So what happens? So naively, this violates the identification A goes to A plus 2 pi and F. Is that the end of the story? No, it is not. The point is that, you see, the essential point is that we have this background field B, but that's not the only background field in the question, in the problem, because that's not the only symmetry in the problem. So before finishing, we should talk about the background field.
Clay, sorry, before you talk about the other background field,
Yes.
I had a small question. The axion coupling that you wrote at the beginning doesn't make sense on non-spin manifolds, right?
I just missed it cut out for a second. Can you say it again?
The axion coupling that you wrote at the very beginning with this coefficient 1 over 32 pi squared.
Yeah.
Yeah, that doesn't make sense on like CP2, right? that only makes sense on spin manifolds.
For SUN, the instanton number 1/8 pi squared trace f wedge f is an integer even on a non-spin manifold.
Yeah, okay, but if PB is still an even, if I remember correctly, PB is still in an even form, no? PB is still an even thing, so you can dismiss the two in the denominator.
Yes, essentially, if you're on a spin
Okay.
manifold.
Okay, so you're not assuming either way.
I'm not assuming either way. No, I'm about
Okay.
to. What I'm about to say works for both spin and non-spin.
Okay, thanks.
More questions, please. I'm going. It seems like I'm going lightning fast, which means that I'm not getting enough questions. I guess we'll have more questions afterwards. Okay, so right, we have this other symmetry. This U1. We have this we need a background field for U1, 2. So such a background field, what should it be? It should be some kind of field C, which is a 3 form. And the action should contain a term, well, just J wedge C, or J wedge star C, what you usually write. So we would put dA over 2 pi f wedge C3.
So Clay, just before that, this PB coefficient is n-1/2n. But I vaguely remember instanton can fractionalize to 1/n, not 1/2n.
Yeah, this is actually closely connected to Zohar's question about spin manifolds. So let's consider the specific case of SO3, just so we can, and SU2, so we're dealing with the smallest possible n. So there's an additional 2 that's in play when you're on a spin manifold. So for SU2, say, instantons are always integer quantized with this notion of instanton number. For SO3 on a spin manifold, they can have half integral instanton number. For SO3 on a non-spin manifold, you can have quarter instantons.
Okay, thank you.
So there's an additional fractionalization by a 2 on a non-spin manifold.
Okay, thank you.
Yeah, I'm not sure. I don't know if that has ever been made sort of great use of, but it's a 2 to keep in your back pocket. Okay, more questions, please.
I think in some 3D literature on 3D dualities, this tool was used heavily for bosonic dualities versus fermion boson dualities.
Oh, you mean, yeah, because you have to restrict to some spin manifold or not in some particular case. Or if you're bosonic, you can be on a non-spin manifold, so much more. Yeah, I see. Yeah, okay, good point. Any more comments, questions? Okay, so we've talked about the background fields for the 1-form symmetry. Now we have this background field for the 2-form symmetry C3, and it couples to dA. And the point of this is that we can restore, we can make the coupling A over 8 pi squared trace f wedge f legal if C3 mixes or is activated by gauge transformations of B. So this is the way to see the mixture at the level of background field. So the invariant field strength is not DC3, but is rather DC3 plus pi over n times 1 minus n Pontryagin of B. So you could think that this is like a Green-Schwarz mechanism. For B and C, these background fields. So if there wasn't this mixture of the symmetries that I was talking about, the gauge invariant background field would be DC. But because there's this mixture, the gauge invariant background field is DC plus this multiple of the Pontryagin of B. This Green-Schwarz mechanism for background fields by another name is called a higher group global symmetry. Okay, so we've got these two fancier ways of thinking about this slightly unusual symmetry. And from either point of view, we can essentially get the inequality that we want now. So imagine this symmetry emerges along an RG flow. So there's some scale where the two-form symmetry emerges. There's some scale where the one-form symmetry emerges. But what we've learned is that once you have the one-form symmetry, that implies you can have it in terms of the defects, background fields, they're really equivalent. Well, one-form symmetry defects fuse to give a two-form symmetry defect. And similarly, gauge transformations for the one-form background fields produce the two-form background field. Therefore, if you have the one-form symmetry, you necessarily have the two-form symmetry. So this implies our inequality. If you flow to Axion-Yang-Mills in the infrared, once you've reached the scale of the one-form symmetry, you have to also be able to activate the two-form symmetry. Okay, so that's the kind of quick and dirty way to see where this inequality comes from. It's really just a statement about the nature of this symmetry group and what's a good subgroup and what's not, right? The two-form symmetry and the two-form gauge transformations close on their own. But the one-form symmetry doesn't. Whenever you have the one-form symmetry, you can make the two-form symmetry. That's the funny thing about this structure of Axion-Yang-Mills. And what I'd like to do now in the last few minutes is explain to you in an example in practice what this kind of thing means and show you the mechanism that enforces it. So I'm not even sure exactly who to attribute such a model to, but I'll put a few initials that enough initials that you can assign names to it to make it seem like a fair assignment of credit. So this KSVZ Axion model, we're going to have SUN Yang-Mills. What else? We're going to have psi plus and minus, which are fundamental fermions. So they're charged under the SUN in the fundamental. And then we're going to have phi, which is an uncharged complex scalar. Okay, so those are our fields. So what is the action in this? So S is an integral. So we've got kinetic terms, which I won't write. The kinetic terms include, of course, the coupling of psi to the gauge fields through the Dirac operator. Then the interesting parts are some Yukawa couplings. And then there's also a potential for the scalar v of phi. Okay, so what are the crucial features of such a model? Well, one thing, oh, and I should say that we'll assume that everything is weakly coupled here. So one important feature is that there's a Pecha-Quinn symmetry. Okay, that's kind of an abusive language, but it has stuck historically. That just means there's an anomalous U1. So psi plus and minus have charge 1 under this, and phi has charge 2. Okay. So the couplings in the Lagrangian preserve this symmetry, but there is an anomaly that violates it. Then we'll also consider a potential, which I'll take to be of the following form. Which will condense phi. Okay, so this model that we're writing down is the UV of the flow. So it's some good renormalizable action. And at long distances, this is supposed to give us axion Yang-Mills. Let me just remind you how that comes about. So phi at long distances looks like F times the exponential of IA over F, where A here will be a pseudo Goldstone boson. Axion. So this is going to be the axion. And the point is that a chiral rotation to remove the coupling between A and plus minus generates the axion Yang-Mills term. Okay, so after doing that chiral rotation, the psi's are massive. We've integrated out the radial mode of phi, so we just end up with axion Yang-Mills. What are the scales? Okay, one of them is easy, E1 form. This is the mass of the fundamentals. And in this model, this is just lambda F. And note that this is much less than F because we're working at weak coupling. So that I can control the whole thing and say what I'm talking about. Okay, so that's E1 form. What is E2 form? So let's look at the string scale. Let's examine the potential. Okay, so the potential, of course, it's got this double well, but it's rotated. So it's I'm not going to try to draw it, but I'll just say rotated, because it's a potential for a complex scalar. So what does a string configuration look like? So in a string configuration, phi winds down here at the minimum, so phi sits, the absolute value of phi sits at the minimum. The phase of phi wanders around that circle that's present there. So this means that the string can unwind if phi can get to 0. So if you have an energy fluctuation where the modulus of phi gets kicked all the way off of the minimum over 0, then it can go over the hump and the string can unwind. Okay, so from this you can estimate E2 form. Okay, so you would estimate that this is the potential, the scale associated to the potential at the origin, which is equal to root mf. So what did we conclude? So our inequality is square root f should be greater than or equal to lambda f. Okay, what does that mean? You might be slightly confused.
Why I'm confused about the square root of mf? I don't understand. Maybe you meant square root of the whole thing?
No, I think it's just because of the way my v evaluated at the origin is m squared f to the 4th, and is 0 at the minimum. So the energy cost of phi getting from the minimum to the origin. So v is dimensions of energy to the 4th. So then I just plug in 0. That's the difference between the minimum and the origin, and I take the 4th.
Your f has dimension 1.
1.
And
Yeah.
and m is dimensionless?
Yes. M is a dimensionless number and lambda is a dimensionless number.
Okay. I didn't realize that m is dimensionless. Thanks.
Yeah. So M is, yes, it's a slightly unfortunate name, I realize, for a dimensionless number. So this is, the F's cancel, and this is an inequality among dimension numbers, root M and lambda. Okay. So you can ask, it's a bit confusing. You could say, well, what happens if this inequality is violated? Nothing seems to be wrong with this quantum field theory. So let's ask, what happens if violated? So what happens if, let's take it to be parametrically the wrong way, lambda squared, much, much greater than m. Well, what you should be careful here. So of course I want it still to be under control. So this will be less than 1. You should be careful here about our semi-classical analysis. And after all, we just sort of willy-nilly said, well, look at this potential, phi has a minimum, ignore all quantum effects, blah, blah, blah. Is that really justified? Well, we can look at the one loop fermion potential in this limit. The one loop potential for phi generated by the fermions. And in this limit here, this one loop potential dominates the classical potential. So this analysis of where the minimum was and what were all the scales becomes wrong. In fact, what happens here, if you chase down, it's just a little one loop calculation. You find that in this limit, the expectation value of phi goes like the U off divided by lambda, which is gigantic. So phi is being frozen out at a minimum that's very, very, very far from the origin. So what does this mean? So of course, the expectation value of phi is what's really setting the effective axion decay constant. So what we see is that in this limit, A becomes non-compact. And decouples from the Yang-Mills sector. So I don't think there's anything mathematically wrong with this limit. It's just that you have to be careful about how we ask the question. We said, if you flow to axion Yang-Mills, then you'll find this inequality here that I wrote. If that inequality is violated, you can't flow to the axion Yang-Mills that we put in as our input. So that's the kind of logic that protects this analysis. Okay, so I'd like to conclude now. Let me just say some further directions that we've explored, but I won't tell you about too much. So the directions are, first of all, you can add matter. So this breaks Zn1, so you might think the whole analysis goes away, but sometimes the flavor symmetry can replace this. And we've also considered some other axion models. And a similar mechanism works in that case, where if you try to violate the inequality parametrically, you drive the axion decay constant to be enormous. Okay, so I'll stop here and we can have more questions and discussion. Thank you.
Okay. So, questions? I have one question. So you started with the mention of the UV completion because this axion theory is non-normalizable.
Yeah.
So what is the picture of all these developments from that point of view?
Well, I mostly view this as an interesting result from the point of view of bottom-up sort of phenomenology. You know, if you're although I myself am not a model builder, I have in mind as a cartoon of a model builder someone who says, "Oh, I'm interested in axion Yang-Mills, and maybe that solves some strong CP problem or something like that." But then they know, okay, it's not normalizable. I want to hypothesize some UV model, some new degrees of freedom. You know, there'll have to be some new degrees of freedom, which will fix up this problem. And this is some kind of model-independent way of thinking about some constraints that one would always find on those new degrees of freedom.
Did you think if there are any implications for these real axion models?
I have not thought about that. That's an interesting question, but I haven't thought about it at all.
I got a question.
I can't really hear you. Sorry.
I got a question.
Yes.
Can you hear me?
Even louder would be great. Sorry.
So can you hear me?
Yes.
Yeah, we can.
Okay. I mean, for the example you illustrated, well, at the end of the day, in the IR, what kind of action potential is generated?
In the end of the day, if you mean if you're trying to violate the inequality?
No, 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 no.
Oh, you mean in this
the
case?
IR, in the IR, in your model, in the IR.
Oh, you mean just in axion-Yang mills? What kind of potential is generated for the axion? Just the standard cosine potential, right? I mean the.
Okay.
Yeah, this is like this axion-Yang mills Lagrangian is sort of the most vanilla possible Lagrangian that I could have considered.
Okay.
So nothing fancy is happening.
Maybe what can I ask one more question?
Yes, please.
Maybe a simpler model that is interesting for various reasons is just BF theory, which is A wedge 3 form.
Yeah.
Sorry, what did I say? I meant A wedge 4 form. So DA wedge 3 form.
Yeah. Uh-huh.
Does that share many of the features of what you said? Because, well, the reason I'm asking, let me just maybe give you some motivation, is that you can think about the eta prime physics at long distances.
Yeah.
In that way. It's basically D eta prime wedge a 3 form gauge field.
Uh-huh. Yeah, I suspect so. Yeah, I suspect so, Zohar, but I haven't thought through all of it, but it sounds very natural.
There is a discussion in the literature of what happens to this 2 form symmetry in the context of eta prime particle.
What is the what are the hypotheses?
It's very analogous to what you talked about.
Uh-huh.
But it's not about this model. It's about D eta prime wedge 3 form.
Mm-hmm.
Which also has a funny 2 form symmetry, which is not a symmetry of full QCD.
Mm-hmm. Which is emergent. Yeah, I see. Yeah, okay. So maybe there is some crosstalk between this kind of analysis and that model also.
Hey, Clay, can I ask a question?
Yes, Qiming, please.
So,
First of all, you have to tell
if
me where on planet Earth are you before you answer the question.
So I'm in Shanghai and I'm actually in quarantine right now.
Okay.
So, okay.
Good
So,
luck to you.
thanks. So if I think of the axion model as compatible by a phi D theory, and so the axion term will be given by a phi D Chern-Simons term.
Yeah.
And could I think of this, I mean, would this 4D anomaly correspond to the phi D anomaly between the U1 instanton number and also the center symmetry of the SU? And there's a recent paper by Boniti et al. They studied this anomaly.
Yeah, that's probably right. Is there some kind of higher group in that example also? Or maybe it just ends up being well, I'm not sure exactly if it will be, if you lift it to one dimension, if it will be just an anomaly.
In phi D, I think it's just a mixed anomaly.
I see.
Mm.
Oh yeah, but right. Okay. Yeah, that's probably right.
I see. Thanks.
Excuse me? Can I ask?
Yeah, please.
Do you think anything analogous can be said to the one-form symmetries acting on the strings in six-dimensional gauge theories? Like the effect.
Yes. Yes. I mean, you mean discrete one-form symmetries?
Maybe the continuous ones acting on six-dimensional strings.
Yeah.
Or...
So indeed. So in fact, some of this stuff was in this recent paper that I had about a month ago or so. I'm not sure exactly when it was. So
with
the
Dumitrescu and Intriligator.
Yeah. So let me summarize related things there. So let's discuss continuous one-form symmetry. So low energy six-dimensional quantum field theories appear to be filled with them because if you have a gauge theory at long distances, you'll have trace F wedge F, which is giving you one form symmetry.
Yeah.
But it's actually not too hard to show that that symmetry cannot be a symmetry of the ultraviolet of the ultraviolet fixed point.
Yeah.
Are you familiar with that?
Yeah.
Yeah. Okay. So so that symmetry cannot.
I think basically your argument was that there's no proper superconformal multiplier which contains that.
Which contains a current, right? Exactly.
Yes.
So
yes.
and in practice, what happens is just that, you know, there's a kind of Green-Schwarz coupling, which is like dynamical B wedge trace F wedge F.
Yes.
And so you can think that Green-Schwarz coupling is like you gauge that symmetry that looks like it's there at long distances. And so it's not really a symmetry in the ultraviolet because you gauged it.
Yeah.
So, yeah, so in any case, so that symmetry is not there. But the other thing is, you could also ask me, can there be some kind of like emergent higher group structure? Can it be that the one form symmetry mixes at long distances, at least mixes with other sectors? And there can be.
You mean even higher form symmetries?
Sorry?
Mixing with, you mean mixing with even higher form symmetries?
No, I meant mixing with lower form symmetries, where it's the top part. There can be, but sort of the principle that there's nothing, that all of that disappears by the time you get to the UV is actually very useful for computing anomalies, because it means that certain like mixed anomalies have to sort of add up with their Green-Schwarz counterparts to be zero.
Yeah.
Because you know that by the time you get to the UV, that structure is gone.
Yeah.
Anyway, this is explained better in that paper, but yes, this kind of reasoning can be used for 6D field theories. I should say that there's also, I mean, if you consider 6D little string theories,
yeah,
the situation is different. In that case, there are these one form symmetries which appear to be there along the entire RG flow, and you can think that their role in life is to measure the conserved string number, even at the fixed point.
Okay, thank you.
May I ask one question?
Yeah.
So is there any like non-trivial tooth anomalies in for these like one form, two form symmetries?
Okay, I found.
Well, I was hoping to hear what Siri had to say about the answer to the question. Yeah, that's a good question. I mean, there's some kind of anomaly between the two form symmetry and the shift symmetry of the axion, which is just the kind of correct form. And you know how, for instance, for Maxwell theory, there's a mixed anomaly between the two one form symmetries. If you change the form degree, the symmetries always change in such a way that mixed anomaly stays there. So there is a mixed anomaly involving that sector of the theory. I'm not sure if that talks in any meaningful way to the one form center symmetry, though.
Okay.
Okay, maybe I'll stop this and we can just chit chat for a little bit.